Hello everyone, here's worksheet number 12, and in this worksheet we're concerned with pressure. How does pressure work? How does it relate to temperature and volume and number of moles in a container? And so to start off, we've got number 1 here where we're being asked to convert 531 torr into kilopascals. So in order to do this, let me first describe to you what a torr is. So 1 torr is 1/760th of an atmosphere. So 760 torr make up an atmosphere. And an atmosphere is just the pressure at sea level, atmospheric pressure at sea level. Well, if we wanted to take this and convert this into pascals, figure out how many pascals this is, we would have to either look up or remember that there are 101,325 pascals in one atmosphere. Okay, so the way this works out is that it turns out that 1 torr, so 1 torr equals 101,325 over 760, just this number here, pascals per atmosphere. And so this just is approximately 133, or excuse me, per torr, 133.3, and the units here would be pascals per torr. So this tells us here how many pascals there are in a torr. And now we have derived the unit conversion we can use to convert from torr into kilopascals. And it very simply just goes like this. We start off with 531 torr, 531 torr. All right, and let's ignore the kilo for now and just solve for pascals. So times 133, we'll just use this approximation, this is good enough. 133.3 pascals per torr. That's what we just solved for here. Our torrs cancel, and we're now left in pascals. And so the number that we get is 70,782.3 pascals. And now if we want to convert this into kilopascals, we just take this and say there are 1,000 pascals in a kilopascal, so our pascals cancel, and now we're left with kilopascals, which give us 70.783 kilopascals, and we can just round to 3 significant figures, which would be right there. So B is the right answer for number 1, 70.8 kilopascals. Now in number 2, suppose we have a cylinder with a movable piston whose volume can change based on the gas inside. If the cylinder has a volume of 0.75 liters at room temperature and a pressure of 760 torr, what would the pressure of the cylinder be if the temperature was increased to 150 degrees Celsius and the volume was held constant? Okay, so here we start out with a movable piston and we're given the volume, but then at the end of the problem it tells us that the piston volume does not change, it's held constant. So this immediately really simplifies our problem, because here if the volume is held constant, then it doesn't really matter what the volume was. And all we want to pay attention to is the temperature that we started with. This is our initial temperature. And the initial pressure that we started with, here 760 torr, it's 1 atmosphere. And then what pressure we're increasing it to, which is 150 degrees Celsius. And we want to calculate what the pressure of the cylinder is once the temperature was increased to 150 degrees Celsius. That's all we care about. We don't care about what the volume of the cylinder is. All that we care about here is that this volume does not change. It's held constant. So the equation that we use for when we're changing temperature and pressure in a container whose volume does not change, remains constant, is the following equation. P1 over T1 equals P2 over T2. And you can derive this equation if you're interested in it. Basically the idea is that as you increase the pressure, your temperature must increase as well. This happens all the time, and a lot of really neat systems take advantage of this principle. So let's start out identifying what P1 and T1 are. P1 and T1 are our initial pressures, pressure and temperature. So the initial pressure is 760 torr. So P1 equals 760 torr. And T1 is 23 degrees Celsius. Okay, let me make a quick mention here, a quick note about the units. Remember how when we were doing M1V1 equals M2V2, so let me take a second here and on the margin write this down. Some people preferred M1V1 equals M2V2. I do C1V1 equals C2V2. Right, and remember how we were discussing units for this equation, where essentially it's just a ratio between concentrations and volumes. And the only thing that mattered with units is that your concentration units be the same on both sides of the equation, and your volume units be the same on both sides of the equation. Okay, so you can do molarity. You could do like 5 molar and 20 milliliters, right? And then you do something like that. You could do 1 molar on this side and 100 milliliters on that side. But it didn't really matter what units they were as long as your units were the same. Or you could do 5 ppm and 20 liters or something like that, you know, and as long as this unit was still ppm and this unit was still liters, you would be okay. So the same way, we are going to treat our units in this equation with P1 over T1 equals P2 over T2. It doesn't matter what the units are here, as long as the units on this side of the equation and the units on that side of the equation are the same. Because this is a ratio, so we want to make sure that our units cancel as well. Okay? So it's very, very simple as long as your units are the same on both sides of the equation. So we're okay working with torr. We don't have to convert to atmospheres. And we're just fine working in degrees Celsius. We don't have to convert to Kelvin or any of that. Just as long as we use torr and degrees Celsius on this side of the equation, which is what we're going to do. Okay, and the last piece of information we're given here is 150 degrees Celsius, so T2 is our final temperature, is 150 degrees Celsius. Now we're ready to solve for P2. So the way I like to do this is first of all start out with solving this algebraically, so I'm just going to take this T2 and multiply both sides to move it over there. So I get this. I'm just going to put this in parentheses. P1 or T1 times T2 is going to be P2. And now I just plug in my numbers. So P1 is 760 torr. T1 is 23 degrees Celsius. And this is going to be times 150 degrees Celsius as T2. 150 degrees Celsius. And now you can see the value of canceling out your units, because degrees Celsius cancel, and the units we're left with in are torr. The units we're left with are torr. Right? So that's why it's important to make sure that your units on both sides of the equation are the same. But it doesn't matter what those units are, because the temperature units will cancel, and you'll be left in whatever units of pressure you had. And so that requires now that the units of pressure for P2 are torr. And so the correct answer then for this is 1,100 torr. And that corresponds to A. So A is the right answer for number 2. Now for number 3, which has the larger molar volume at STP? So what we're saying with molar volume is it's the volume that's occupied by 1 mole of the ideal gas at STP. So STP stands for standard temperature and pressure, and those are defined as 101.325 kilopascals and 0 degrees Celsius. So we're going to assume that all these gases here behave as ideal gases. And so suppose we had 1 atmosphere, 101.325 kilopascals of the gas in a container at 0 degrees Celsius. What that would mean is that all ideal gases are going to occupy the same volume, and that volume is 22.4 liters. Okay, so D is the correct answer for number 3. So 1 mole of the ideal gas takes up 22.4 liters. Alright, so if I had a mole of hydrogen at 1 atmosphere in a container at 0 degrees Celsius, I would have 22.4 liters. Same thing for helium, same thing for fluorine, and any gas that behaves ideally will satisfy this property at standard temperature and pressure. Okay, so D is the right answer for number 3. Now in number 4, we have a certain gas, and we're being asked to determine how many moles of that gas do we have if it's contained by a container that is 0.7 liters in volume at 24 degrees Celsius with a pressure of 750 millimeters of mercury. So let's take a second here and first of all identify what kind of an equation we can use. If we're given the volume, the temperature, and the pressure, and we're trying to solve for moles, the best equation to use here is one that has all those variables, and that happens to be our favorite ideal gas law. PV equals nRT. Because we have pressure, and we have volume, and we have obviously the universal gas constant, and the temperature. Those are given to us, and so we can very easily solve for moles. Now, I want to make a quick note before we dive into this about what R is, because sometimes you can use R equals 8.314, and then other times you can use 0.08206, and it's sometimes hard to figure out which one to use. And this is where units come in really handy. This is also an example of a situation where units, if you show units, you'll never mess up. But if you skip showing units, you have pretty much a 50-50 chance of picking the right constant. And that's also a 50-50 chance of picking the wrong one. So here's the foolproof way of knowing which constant to use. The 8.314 constant for R is in joules per Kelvin mole, or joules per mole Kelvin. Okay, so if you have joules in there, and Kelvin and moles, then you can use that equation. In this situation, we're going to be using a slightly different set of units. If you want to use, and this is the one I'll write down, R equals 0.08206. If you want to use this R, then the units for this R are liters, atmospheres, per mole, Kelvin. Okay? So liters, atmospheres per mole, Kelvin. That's the unit for R. Now let's see. We have liters, so we can use liters. We have atmospheres here in R, and we have millimeters of mercury here in the problem. So we have to convert this into atmospheres, which is thankfully very easy. And we have moles, so moles is what we're trying to solve for. And we have Kelvin here in R, so we have to figure out how to convert 24 degrees Celsius into Kelvin before we can use this R. So let me go ahead and do that first. 24 degrees Celsius in Kelvin is going to be 24 plus 273.15, and so that temperature turns out to be 297.15 Kelvin. So now we have Kelvin, and 750 millimeters of mercury, so then 750 millimeters of mercury converted into atmospheres goes like this. 1 atmosphere is 760 millimeters of mercury. Millimeters of mercury cancel, and so the pressure that we end up with is just 750 divided by 760, equals 0.987 atmospheres. Okay. Now we can use this R, the universal gas constant, because we have liters, we have atmospheres, that's right here, we have moles, that's what we're trying to solve for, so that'll be in moles, and then Kelvin is shown right here. Now if we just solve for N, because number of moles is N equals PV over RT, then it goes like this. And we just plug all of our variables in. Pressure is 0.987 atmospheres. Volume is 0.70 liters. Let me leave R out for a second and just plug in T here. So T is 24 degrees Celsius. We converted that into Kelvin. It's 297.15 Kelvin. Okay, and then N is obviously going to be in moles because it's the number of moles of gas. And here's our R. 1 over, right, because it was down here on the bottom, 0.08206. And the units for that are now going to be reciprocated because R was on the bottom, so it's 1 over R. And so the units here end up being moles Kelvin over liters atmospheres. Okay. All I did is I just flipped this upside down, reciprocated it, because now my R was on the bottom. Okay, so this is R. And now what I'm showing here is that I can cancel units. Atmospheres cancel, liters cancel, and Kelvin cancel. And what are we left with? Moles. Right here, moles. So this matches our units for N, because N is going to be in moles. And so the answer that we end up with when we do this just in our calculator, so we go 0.987 times 0.7 divided by 297.15 times 0.08206. The number that we get is 0.028 moles. Okay, so with moles there, if we wanted to convert into millimoles, we just go times 1,000, and so we're left with 28 millimoles. Okay, so all I wanted to show here with the R is that if you choose the correct R, which you will always know the units of, and so you just choose the units in such a manner that it corresponds to the units given in the problem, then you can show how your units cancel when you plug all of your numbers into the ideal gas law and confirm that the units you get out are indeed the correct units for the variable you're trying to solve. Okay, here we demonstrated that atmospheres cancel, liters cancel, and kelvins cancel. And the units that we're left with from the ideal gas constant are moles, which checks with what we're trying to solve for, because we were trying to solve for the moles of gas. Okay, so that's the surefire, foolproof way of figuring out what R to use. Look at the units. And it's really another opportunity for me to emphasize how important the units are. Please show your units. It will save you a lot of trouble. Okay, so A is the correct answer for number 4. So here in number 5, we've got 7.3 grams of fluorine gas in a container at a pressure of 3.1 atmospheres at 37 degrees Celsius. And we're being asked to determine what is the volume of this container. What volume does this gas occupy? So I went ahead and did a couple of things ahead of time. I calculated the number of moles of fluorine, so I just took 7.3 grams, divided it by the molar mass of F2 right off of the periodic table, got my moles, and then converted degrees Celsius into Kelvin, so that my units here, moles and Kelvin, and atmospheres correspond to the universal gas constant that gives me liters for my volume. So the gas constant we're going to use is the same one we used up here for R, and number 4, and R is 0.08206 liters atmospheres per moles Kelvin. Okay, so let's go ahead and use the ideal gas law. So we start out first with PV equals nRT. And we're going to this time solve for volume because that's what we're trying to find. I like to solve for the variable algebraically first. You can plug in the numbers first and then move them around to get your volume. I like to do it symbolically first. So that way I just go ahead and plug my numbers in and I'm already done. So I'm going to divide both sides by P. And I'm going to isolate my V over here on this side and show that V is the number of moles times the universal gas constant times the pressure divided, or times the temperature divided by the pressure. And now I can just plug all of my numbers in. N is this 0.192 moles. R is now 0.08206 liters atmospheres. Liters atmospheres per mole Kelvin. And then my temperature is this right here. Why don't I just go ahead and include that in there? And all of that is over my pressure. And the pressure is 3.1 atmospheres. And we're already in atmosphere, so we don't have to do anything to the pressure. Let me make that line a little bit straighter. There we go. 3.1 atmospheres. Okay, and let's make sure our units cancel so they make sense. Moles cancel. Atmospheres cancel. And Kelvin cancels. So the units we're left with are in our liters. So what we see here is that when we calculate everything out, we see here that we are left with 1.57 liters, or just simply rounding up to 1.6 liters of fluorine gas. So D is the correct answer for number 5. So here in number 6 we have 13.0 grams of chlorine gas in a container with a volume of 1.1 liters at 25 degrees Celsius. And here we're being asked to determine what the pressure is in millimeters of mercury. So I did a few things ahead of time, just like in number 5, because a lot of these problems have a lot of things in common. So I'm just streamlining the steps for you so we can really spend time focusing on the important differences between these problems. So I went ahead and calculated the moles of chlorine gas. That should hopefully be an easy step for everybody. And then converted Celsius into Kelvin. And our R, universal gas constant of choice here, is one that uses the units we're interested in. So we got moles and Kelvin and liters. So the clear choice here is going to be 0.08206 liter atmospheres per mole Kelvin. That's our choice for R. And now let's come here to the ideal gas law. PV equals nRT, and we're interested in the pressure because we're solving for pressure. So we divide both sides by V, the volume, and we get pressure equals number of moles times the universal gas constant times the temperature divided by the volume. And at this point, we can just plug our variables in. Number of moles is given here as 0.183 moles. And then the universal gas constant, which is 0.08206, we can plug in there. Liters, atmospheres per mole Kelvin. And then we can include our temperature. And our temperature is 298.15 Kelvin. Okay. So now that we have those three variables in there, we can divide by the volume. Dividing everything by the volume, and that was given in the problem as 1.1 liters. 1.1 liters. And let's take a moment and make sure that all of our units cancel. So we have moles and moles. liters and liters, Kelvin and Kelvin. And the last unit that's left is atmospheres, and this is the unit of our pressure. So notice it's not in millimeters of mercury, it's in atmospheres. So in atmospheres, when we do this calculation, the pressure that we get is 4.07 atmospheres. And the way we convert from atmospheres into millimeters of mercury is by multiplying this number, here 4.07 atmospheres, by 760 millimeters of mercury per atmosphere. And we see here that the atmospheres cancel, and we're left with millimeters of mercury. 3,096 millimeters of mercury. And converting this into scientific notation, really tying a lot of concepts here, we end up with rounding it to 2 sig figs because we have 2 right here in our measurement of 1.1 liters. And that leaves us with the correct answer for number 6 being B. 3.1 times 10 to the negative third millimeters of mercury. Now in number 7, we're given 5 grams of argon with a volume of 0.65 liters and a pressure of 3 atmospheres. And we're being asked to determine what its temperature is in Kelvin. So I've done a little bit of the legwork already. I've converted the grams of argon into moles of argon, and I've already established that we're going to use the 0.08206 universal gas constant for R. And the reason why is because we've got moles, and we're going to have Kelvin here, and we have liters, and we have atmospheres. Okay, so that's the appropriate R value to use. And now let me use the ideal gas law. And since we're looking for temperature, we want to solve for T. We want to divide both sides by nR. And so in doing so, what we get is temperature equals pressure times volume over number of moles times the universal gas constant. And just like with all the others, let's plug our numbers in. Pressure, the pressure is 3 atmospheres. Volume, the volume is 0.65 liters. N, which is the number of moles of gas we have, we solved right here, 0.125 moles. And here's our favorite universal gas constant, 0.08206 liters, atmospheres, per mole Kelvin. Okay, so what's happening here? Because this is on the bottom, if we were to bring this up, bring this R value up into here, which I can show by just erasing this from the denominator and kind of showing it separately on its own like we did in number 4. What we do is we reciprocate, or we flip around the units. So instead of liters, atmospheres per mole Kelvin, it's going to be the opposite. Moles Kelvin per liter atmosphere. So if R is on the bottom, and you want to keep track of units, you've got to flip the units around too. Okay. So now we see that our liters cancel, atmospheres cancel, and moles cancel. And lo and behold, our temperature is in units of Kelvin. Very nice. So what we see here is that when we do this calculation, 3 times 0.65 divided by 0.125 times this number, 0.08206, then what we get is a temperature of 190 Kelvin. So B is the correct answer for number 7. Here in number 8, we have a nitrogen tank with a volume of 40.1 liters and a pressure of a whopping 13,890 kilopascals at 25 degrees Celsius. Here we're being asked to determine how many grams of nitrogen gas are present. So in the equation PV equals nRT, there's no real place for grams, but what we do have is moles. And so what we can do is solve for N, where we just divide both sides by RT, and N here, N equals PV, pressure times volume, over over R, I messed that up, over R, universal gas constant times temperature. Okay, so we had to do a couple of things. Here we had to convert the temperature into Kelvin so that we can use this R value, and we had to convert the pressure from kilopascals into atmospheres, and that's how you do that. So once we've done that, and we have converted into units that correspond to our universal gas constant, then we can plug in our numbers and solve for moles. So N, which is our number of moles, is going to be the pressure, 137 atmospheres, times the volume, which is 40.1 liters, divided by, and I'll write T down here, our temperature is 298.15 Kelvin, and I'll write my R over here. I don't mean to confuse anybody by doing this. I mean, R it's the same thing as putting it down here on the bottom. But what I'm showing here is the units, where the units flip around, where we write the reciprocal of the units. Okay, so this is our R value. And in doing so, what I can demonstrate is that the units just cancel. Okay, so when you're calculating this out, you can just keep this on the bottom. But this, I think, shows a little bit better that the units can cancel. And it also shows what units we're left with on the top, on the numerator. So these are the units for N moles, which is good, because that's what we wanted to get at the end. So when we do this, what we find is that we have 224 moles of nitrogen gas. So the last thing to do here, let me move this up a little bit. So the last thing to do here is just take this and multiply it by 28 grams per mole of nitrogen. So what this does is this now gives us grams. And so the grams that we get are 6,290 grams of nitrogen. Okay, and so in scientific notation, that would give us C. So C is the correct answer for number 8. So here in number 9, we've got a football team that's playing a game where the temperature outside is 0 degrees Celsius. Before the game starts, the ball was measured at 14.0 pounds per square inch, just PSI, at 25 degrees Celsius. So, you know, the temperature inside a room, room temperature. What is the new pressure inside the ball after the game has begun? So here we're going back to this equation, P1 over T1 equals P2 over T2. Same equation we saw earlier. And P1 is the pressure that we began with. It's 14.0 psi. And T1 is the temperature we begin with, which is 25 degrees Celsius. And remember that we can use whatever units we wanted as long as the units are the same on both sides of the equation. So the temperature we end with is 0 degrees Celsius. Oh, there's a problem now. Okay, so in this situation, where we have 0 here, that doesn't really work. Because then if you multiply anything by 0, it just turns out to be 0. So it doesn't really make sense. So here's what we can do. If we see a situation like this where our temperature drops down to 0, then this is a situation in which the equation won't work for us. So here we have to convert our temperatures into Kelvin so that we never deal with multiplying something by 0 and getting 0 for an answer, because certainly that would not be a correct answer. So let's go ahead and convert these. So T1 is going to be 298.15 Kelvin, and T2 is going to be 273.15 Kelvin. Okay? We could have done this in Fahrenheit or any sort of unit we wanted, just so long as they would never deal with multiplying something by 0. So we have an initial pressure, initial and final temperatures, and now we can solve for P2. So I'll go ahead and just isolate P2 by multiplying both sides by T2. So P1 over T1 times T2 equals P2. And now let's plug in our numbers. P1 is 14.0 psi. T1 is 298.15 Kelvin. This is now going to be multiplied by our second temperature, which is now lower, 273.15 Kelvin. And we see here that Kelvin cancels, so the temperature units cancel, and the units we're left with are psi. So when we do this in our calculator, what we find is that we get 12.8 psi. So B is the correct answer for number 9. Okay, and so then lastly for number 10, we've got hydrogen peroxide decomposing into water and oxygen. According to this equation, so we got 2 moles of hydrogen peroxide decomposing into 2 moles of water and 1 mole of oxygen gas. So how many liters of oxygen gas are formed at 1.2 atmospheres and 30 degrees Celsius if 15.7 grams of hydrogen peroxide are allowed to decompose? So anytime we have a balanced chemical equation to work with and we're trying to figure out how many liters of gas we produce, we have to first of all figure out how many moles of gas we produce. And that can be figured out based on how many moles of reactant we had, reacted. So we reacted 15.7 grams of hydrogen peroxide, and I went ahead and used its molar mass to figure out how many moles of hydrogen peroxide we reacted. And now we can use the balanced chemical equation to tell us how many moles of oxygen gas were produced. So we know we reacted 0.462 moles of H2O2, and then 1 mole of oxygen gas is produced when 2 moles of H2O2 are consumed or reacted. Now moles of H2O2 go away, and we are now in moles of oxygen gas, so which are 0.231 moles of O2. Now, since we have moles and atmospheres and degrees Celsius, which we can convert into Kelvin very easily, we can use the ideal gas law to figure out what volume of oxygen we produce. PV equals nRT. And now we want to solve for volume, so we divide both sides by P. So the volume equals number of moles times the universal gas constant times the temperature divided by the pressure. So we have everything we need now. So V equals the number of moles, which is right here, 0.231 moles of oxygen times 0.08206 liters atmospheres per mole Kelvin times the temperature. Temperatures in degrees Celsius, no problem. We just take this and convert it into Kelvin. So 273.15 plus 30 is going to be 303.15 Kelvin. Now all of this we will divide by our pressure. And the pressure is given to us as 1.2 atmospheres, divided by 1.2 atmospheres. And let's check our units just to make sure they all cancel. Moles cancel, atmospheres cancel, and Kelvin cancels. And we are left in units of liters, which is perfect because that's a great unit for volume. So when we do all of this, so 0.231 times 0.08206 times 303.15, divide all of that by 1.2, we get a volume of 4.78 liters. Okay, so now let's round that to two significant figures, and so the answer we get is D, 4.8 liters. So that's how many liters of oxygen are produced when you react 15.7 grams of hydrogen peroxide with those conditions. So there you go. You can use a balanced chemical equation to figure out how many moles of oxygen are produced, and a set of conditions that you can plug into the ideal gas law to figure out the volume that oxygen will occupy. And there we go. That was worksheet number 12.